Welcome. So we are going to look at some digital sequential logic circuit design tutorial or exam questions. So this one is asking to construct a digital sequential logic circuit using a JK flip-flop. So it starts with asking us to uh, construct the excitation table based on the truth table. But to begin with, let's just go ahead and construct the truth table itself by ourselves. So first, we know that JK flip-flop has two inputs, right? J and K. And there is a input Q, T as well, right? So this is the state of the JK flip-flop in the current timestamp. And based on these three inputs, we will be determining what is the output at the next timestamp T plus 1. Okay. So all three are actually working as a input to determine what is the output state. So that's our truth tables configuration, and because these all three are important to us, we will have 8 combinations of these values. So let's just complete the table. So state could be 0, 1, and yeah, I'm going to just complete the table here. Okay. So this is the standard configuration for all the configurations which can be there in any type of situation. Okay. So at each of these situations, let's see what is the Q T plus 1 going to be. So if J and K are 0, right, as given in this first two configurations, it will just remain the same state, right? It will preserve the same state in the next timestamp as well. So that's the nature of the JK flip-flop. And if the K is set but J is 0, in that situation, no matter what actually the current input is, or current state of the JK flip-flop is, we will be having a reset, right? So K is acting as a reset, so we will have a 0 here. So this also actually, even though we mention it here, it doesn't actually matter in this case. If the K is 1 and J is 0, we will be setting it to 0. Okay. Here it's the opposite. So we have a 1 here at the J, which means it's going to set the value to 1 uh, as far as K is 0. Okay. So these two will be 1. How about this one? So there are both J and K are 1 here, and what that means is the toggle configuration of the JK flip-flop, or we call it T flip-flop as well. So here what we have is that we will toggle the value, whatever the value available in the current state will be changed. So here it's 0, whereas the J and K are both 1, which means it's going to toggle to 1. Similarly, when we have 1 here and JK are 1, that means we are toggling from 1 to 0. So this is the JK flip-flops uh, truth table. So what is the excitation table? So excitation table is about we need the current state. I mean, we need to take some kind of uh, change in the state of our flip-flop, right? The value of our flip-flop we need to change in some particular way. So what are the inputs we can set to get that? So that's the excitation table. For example, let's say we have a qt and we need to go to a new state at the next time interval, right? So there could be, now it is a single variable, right, single value, single bit, so we can have either 0 or 1 there, right? If it is 0, we can go to 0 in the next state, next timestamp as well, or we can go from 0 to 1, right? Other ways. If the current state is 1, we can go to 0, or we can go from 1 to 1 as well. So in this type of these are the exhaustive combinations we can have, or we need to have in our particular circuit. So in order to achieve this one, what are the configuration of J and K we need, right? So that's the excitation signals, right? J and K. So what are the values we can set in order to get this type of transition? So you can refer to this table and figure out what are the occasions this occur, right? From 0 to 0, you can see it occurs here, right? In the first one, and here also it occurs, right? But if you just look at the in this row and this row, right? So here you can see that both. So if you consider only these two signals, right? This one and this one, you can see the only constant is that J is 0, and K actually does not matter if we need this transition, right? What matters is J must be 0. So J is 0 and K is we don't mind, right? So that's the way, because we are going from 0 to 0, right? 0 to 0. If we need to achieve this transition, K does not matter, but J must be 0. How about 0 to 1? So is there any other places we can find a transition from 0 to 1? Here, right? Here 1. Is there any other? Here. Okay, so let's consider this one. So you can see these two configurations, right? This one and this one. So if that is the case, then as you can see, J must be 1 and K does not matter, right? J must be 1, K does not matter. So how about 1 to 0? 1 to 0 transition. So there is a 1 to 0 transition here, right? Then there is a 1 to 0 transition here as well. So here you can see K must be 1, J does not matter, right? J is changing, but K must be 1. So J does not matter, K must be 1. So one more configuration is remaining. If you want to go from 1 to 1, right? There are two situations here, right? This one and this one. There you can see K must be 0, right? K must be 0. J does not matter. J does not matter. K must be 0. Okay. Does this make sense? So you can see whether it makes sense, right? If you want to go from 0 to 0, right? J must be 0, right? Because it cannot be set, right? J is the signal to set, right? But we cannot set if we need to go to 0, right? So it makes sense. You want to go to 1, it makes sense. J must be 1, right? This one actually doesn't matter, right? Because if it is 1, it will be toggling, right? It's the same as going to 1, right? If it's 0, it's going to 1, it means it's toggling, right? So it does not matter. So 1 to 0, so K must be 1. So it also makes sense. 1 to 1 means we are not going for 0 anytime. So it is K must be 0, right? So this is the excitation table for JK flip flop. Okay, so first part is done.